and I will explain how to operate my free and open source calculation program, which can calculate properties of optical reflection from multilayer structure, properties of surface plasmons, which propagates along metal dielectric interface, and properties of optical waveguide, which waveguide modes propagate in waveguide core. In each case, each layer may consist of many sublayers of different refractive index. Number of layers can be thousands of millions, so it's okay. Also, any distribution of refractive index along structure is possible. I see three merits of this program. First merit is the calculations is rigorous. It means that no any approximation or simplification has been used. The calculation is valid as far as the Maxwell equation are valid for your structure. It means that you don't need to worry if you have a rather complex structure that calculation ever hit any limitation because of approximation or something else, or that you will have any systematic error because of your complex structure. The second merit is the calculation of waveguide mode, plasmon, and optical reflection on base of same calculation core. It means that the calculation which is verified for one structure is certainly valid for another structure. It's very useful when you have complex structure and not fully trust your calculations. And third merit is absolutely free and truly open source. A user can look at and understand the programming code, and user can modify any parts of the program and as she wishes, and user can use part of it for its own program. Now I will explain how to download and install the program. First, to go to the content of my website. The link will be in the description below, and go to the download program section, and from here you go to rigorous calculation section and push this zip file to download. It will do very quickly. When it's finished download, just click on it and just drag all the files and directories in a directory of your wish where you will use this program. Just select everything and copy. It's copy rather fast. In the main directory there are 6 files, 3 executable files and 3 Labview files with the same name. If you don't have Labview installed on your computer, you can run executable file, but for this you need to install Labview library. It's free, and how to do it link in description. So you can start executable file, just run, and you can start the program. But if you have Labview, it's better to start from Labview environment, and you just push here, it can start, same program will run. This is short intro how to calculate waveguide. So again you start waveguide program, and here you can see the structure of waveguide core, cover and clad. Each of them can consist of many layers, and it is a number of layers, and presently each one consists of only one layer. This is all gas, name of material, this is thickness, real and complex part of refractive index. Here you can calculate, change one parameter and see how the loss and effective refractive index changes with that parameter. You can change thickness of any layers, refractive index, absorption, and wavelength. For example, also you can change wavelengths. You can change, for example, 1000, and you see the refractive index has changed. Now back. Yeah, again it is changed. Here you can scan one of the structure parameters, for example thickness of one of layer, refractive index, absorption, or wavelengths, and see how the effective refractive index or absorption change with wavelengths. For example, let's introduce some small loss in the core layer. Yeah, calculate. When it's green, means the solution is found, and calculate scan. For example, we will scan this thickness of this layer from its current value to, say, yeah, thinner value. Yeah. Okay. Yeah. So it's calculated losses as the core layer becomes thinner, more field go out and losses decrease, and refractive index also decrease. So you can, for each point of the scan, you can calculate field distribution. For example, let's use this TM, and here's T. So calculate field. So it's for each point, it's calculate the field. And for example, if we increase number of graphs here, and we can scan here, go up and down, and see how the field is changing. You see, each point we press, we go for different thicknesses. For example, now thickness 660, and we draw a different column in the different field, so we can compare how it is changing. For example, let's come back to 1. It's too many points. Let's make less point, like 5. And calculate now. So now change is larger. So you see, you can compare how field distribution change when the thickness changes. So now I will show you how to set layer. At present, this is just one layer per core, per cover. It's rather simple structure. So if you need more complex, for example, for cover, just put here, push here, and here again you can see our structure. So we can increase numbers of layers. Let's increase to 30, for example. So now when you increase, you just set empty layers for 30 layers, and so force, it's L gas always. So we can set material. There's several options. First option from file. So just push, and you see this is many material which I already input. For example, we can set aluminum antimonite. So after that you can see what this is data. It's this K. So imaginary part of refractive index and refractive index of indium antimonite from that file. File is in the refractive index directory. Yes, each file is just set of three data. First is the refractive index, wavelengths, real part of refractive index, imaginary part of refractive index. 90% of refractive index data have downloaded from this website, refractive index info. There's a huge number of refractive indexes of materials, so is like a data like this, list this data set of data, or by some formula. So if you need some specific material, you can download and copy in this directory. So once again, when you choose your material from file, aluminum nitride, it's appear in this box, means the current material with the aluminum nitride thickness. You can put, for example, let's put only 10 nanometers, and its refractive index. Also it's put with dispersion, so as dependence of wavelengths. And next you should set it into your structure. So that is a 2 number. That means which is first number you will start, and which step it will start. For example, I want to start from layer number 2 and repeat each second step. So each third step, yes. So I put like a 3. When I push, so it starts from layer number 2. Next it's miss 2, and so 2, number 5, number 6, number 7, number 8, and so on. So for example, we want a different material, aluminum antimonide, to set from 0, and also number 3. So set layer. As you see, aluminum nitride, and we want like 20 nanometers thick. So we have aluminum 20, 1, 2, 3. So next here aluminum antimonide, and next example gallium nitride. And this one, for example, from first, and so on, and each third layer. So we set all layers like periodically. It means here aluminum antimonide, gallium nitride, aluminum nitride, and again repeating very much. So as here we can push plot layer. It will plot refractive index. Okay. Yeah, we better to use only one graph. So plot refractive index of whole structure. So it's from 0 to 500, and that is the loss, that is absorption. By the way, you can change how you represent loss here. For example, decibel per millimeters. Plot. So yeah, it's in decibel per millimeters. So it's how many decibel light will experience absorption after passing 1 millimeter in this material. So, and for example, it's always 3 material repeated, but for example, if you want to put defect somewhere around, this is 25, example 25 yeah, let's put some another material like ITO, for example. And we want to set this only 25 and only 1 point, no repeating. If I left something, it will repeat to the end. So set layer, so it's on 25, so you don't see any only one layer. And if we plot it, you see we have on 25 we have ITO. So you can put like 100 or 1,000 such periodical layers. And if you push this layer, you see all these layers is already in the cover layer. Yeah, you can redraw and see the real distribution of refractive index and loss. Again, you can use some more convenient unit of your structure. Yes. Well, let's change refractive index of core layer and yeah, put yeah, also it can calculate the refractive index from formulas, and you have some choices here. So some simple material can be fitted by dispersion formula, so you don't need input number by number, just put the formula. Also you can input from parameter like all gas. I already have. You just can put like 0.8 and you see the gas 0.8 and its refractive index, or 0.2. Or from formula, for example, M0. So for this layer, let's make say 100 layers, and M0 will set from 0 and its second layer with thickness, so half 100, yeah, or 5 nanometers. So we have M0 here, and let's compare another. Let's input another material, let's say aluminum oxide, and we also can compare refractive indexes and losses of these two materials. So put, for example, 2, and from formula, so that is aluminum oxide white and previous M0 red. Also, yeah, we can increase wavelengths, maybe once more as M0. Oxide ordinary and extraordinary, refractive index ordinary. Yeah, so for core wavelengths we can compare, and we set as a even number M0, so put an even file, so put 1 here, repetition rate 2 still, so aluminum oxide, and let's plot it. Yeah, many layers. Okay, sad. And with this one, let's make it simple. Let's put M0 here as well. So certainly we don't need so many, only one. And M0 here. So only 0. No repetition. Set layer. I don't know. From formula. Set M0 now. Okay, and let's put M0 here as well. Already there. So M0. By the way, for the last layer of waveguides, the thickness does not matter much. It's just thickness for which the field is calculated. So, but it does not influence refractive index or absorption. It's regular calculation, so it's calculated for infinity. Okay. So next, let's calculate it, this complex structure. So if we just put calculate, it does not show anything because it's based on suggestion which we have here. So for suggestion we have a several choice, so let's suggest and calculate now. So now it's found everything for this layer, and we can calculate field. Well, let's put 2-1. Yeah, field is rather complex, especially for TM mode. And we can scan, but scan, for example, only thickness of aluminum oxide. So it's a scan core number, same story, number 1 and repetition 2. So we change the thickness, and we change thickness from 5 to 10, for example. From 5. So core layer starting from 1 aluminum oxide, and repetition is second one. So push calculate scan. So it's a calculated. You can use more points. It's just 0, so very small number. So, and refractive index like this. Yeah, you can calculate field scan, maybe more points. So when you see, you can see how distribution of field change when, yeah. Next, short intro about calculation of plasmon. So let's close waveguides, just stop, close, and open plasmon. Yeah, start. Yeah, in this case it is the upper part is metal, for example silver, and down part is dielectric. Now Si2 plus silicon. So you just push calculate again. It's found. It calculates skin depths. Also field. You can use either logarithmic or not logarithmic. Low should be logarithmic. And skin depths is also as you can calculate scan. For example, let's change metal to gold. And it's large layer, so thickness does not matter much. Okay, we can just small just for fill. So it's a gold. Calculate. Calculate field. Yeah, you can scan as well. Next is here calculate reflection. So we close plasmons and start reflection. yeah, here's only one layer, but there's also top layer, which usually air, but if you use prism, you can input prism, and transmission is the last layer when this layer is going. Also, you can use with this set, you can use last layer there for convenience if you put here. So you can immediately, so now what is it? Now we have MJO side 2 with such refractive index and air and air from both sides. We can calculate reflectivity and transmission for both layers. It's immediately calculate also field distribution for this incident angle and this wavelength. And we can scan, for example, wavelengths, say from current 1 to 700. So that is white for T and red for TM. Or it's function of incident angle, for example. Let's start from 0 normal to 90 degree, and that is reflection Brewster angle. Anyway, and similar when you calculate scan, you can scan the field over your structure, similar as for waveguide. See how it's changed. And here you can input your input polarizations. For T polarization, TM calculated, but you can input some fixed polarization, like angle between TTM, which is 45, and means equal TTM polarization, and phase difference between them 90 degree means that is a circular polarization. And you can calculate some like a reflection, many parameters. For example, reflection, if you change, for example, you scan phase between them, like you scan using photoelastic modulator from 90 to, and you calculate, and you have a response like this with parameters. So recover change reflection like this. So this is end of short introduction.